Welcome to today's Explainer. We're going to do something genuinely fascinating today. We are going to construct a single, coherent mathematical model that completely bridges the gap between 8th grade geometry and high school trigonometry. These aren't isolated subjects, even though they sometimes feel like it. So our focus today is titled Similarity and Trigonometry, and we're going to connect similarity transformations, right triangle relationships, the Pythagorean theorem, and unit circle reasoning all through one unified lens.
Okay, let's take a quick look at the blueprint of the unit circle. We'll hit Section 1, the foundation, Section 2, the transformation, Section 3, sine, cosine, and tangent, Section 4, special right triangles, Section 5, the unit circle model, and finally Section 6, recap and transfer question. Let's get right into it.
Section 1, the foundation, building a right triangle.
So, we're starting our digital geometry workspace by creating the absolute foundation of our entire model, a simple, rigid right triangle. Everything we do today is going to be built right on top of this one basic shape. Using some basic digital tools inspired by our GeoGebra source, let's map this out. We literally just drop our coordinate points, connect them with line segments, and boom, we form a closed right polygon, a right triangle. This is that foundational geometry you first run into in the 8th grade.
And building this perfectly illustrates the first major rule for our triangle's foundation, the Pythagorean relationship that governs its three sides. You know this one. If we know the lengths of the two legs, we can always find the hypotenuse using the Pythagorean theorem. It's a static, absolute rule for this shape. But hey, what happens when we want to make things a bit more dynamic?
Section 2. The transformation, dilations, and similarity.
Right, now we move from static geometry to dynamic transformations, specifically dilations that create similar figures. We're taking that rigid 8th grade shape and injecting some life into it. Imagine stretching or shrinking our triangle. The side lengths get longer or shorter, sure, but the core shape, it stays absolutely identical. When we dilate this triangle from a center point with a specific scale factor, the figure remains fundamentally proportional. We call these similar triangles.
Okay. Time for pause check number 1. I really want you to think about this for a second. If we apply a scale factor of 2, meaning we completely double the lengths of the sides of our right triangle, do the interior angles double too? Take a moment to chew on that. Well, the crucial point here is that they don't change at all. Similarity transformations preserve angle measures perfectly. According to the angle-angle criterion for similarity, you could make a right triangle the size of a skyscraper, and if it's a dilation of our original triangle, those corresponding angles remain exactly the same. The size changes, but the angles, they are completely locked in.
Section 3. Sine, cosine, and tangent ratios arrive.
Because those angles stay exactly the same while the overall size changes, the relative ratios of the sides remain perfectly constant. And that right there gives birth to trigonometry. We have to engage in mathematical practice too from our standards here and make a mental leap. We're essentially taking our visual understanding of similar triangles, shapes growing and shrinking, and turning them into concrete, abstract numerical side ratios that we can actually calculate and use.
These fundamental trigonometric ratios are literally just the predictable side proportions guaranteed by similarity. Because those interior angles are locked, the ratio of the opposite side to the hypotenuse is always going to be the same for that specific angle, no matter how massive or tiny the triangle is. We just decided to name that specific ratio sine. And the ratio of the adjacent leg to the hypotenuse, we named that cosine. See, trigonometry isn't magic. It's just the standardized language of similar right triangles.
Section 4. Special right triangles, standardizing the ratios.
To make these abstract ratios highly useful in our everyday math toolkit, we need to anchor them to specific, predictable patterns. We do this using what we call special right triangles. By evaluating specific radian and degree angles, like pi over 3, pi over 4, and pi over 6, which are your 60, 45, and 30-degree angles, we can determine exact geometric values for sine, cosine, and tangent. Instead of calculating from scratch every single time, we use these special right triangles as standardized reference points. They're kind of like the universal measuring sticks we can rely on when analyzing periodic functions later.
Section 5. The unit circle model, the ultimate tool.
All right, here's where it gets really cool. We are taking everything we've built, placing our triangle's vertex right at the origin of a coordinate plane, and locking the hypotenuse. We are upgrading our model to its final form. By forcing the hypotenuse to be exactly a length of 1, the math simplifies beautifully. Suddenly, the x and y coordinates of our rotating triangle's far point instantly become the exact cosine and sine values for that angle. We just spin that triangle around the origin counterclockwise, and the point where the hypotenuse touches traces out our unit circle. We've literally taken a static triangle and turned it into a continuous rotational tool.
Let's pause and test our model for our second pause check. You've likely seen this classic trigonometric identity before. Sine squared theta plus cosine squared theta equals 1. Based on the physical model we literally just built, why does this always add up to a perfect 1? Think about it.
Well, it's just the Pythagorean theorem again. Remember our foundation? A squared plus b squared equals c squared? In our unit circle, the legs of our right triangle are quite literally the sine and cosine lengths. Since our hypotenuse, which is the radius of the circle, is locked at a length of 1, well, 1 squared is simply 1. It's the exact same 8th grade geometry concept, just wearing high school trigonometry clothes.
And this brilliantly illustrates how the unit circle becomes a true mathematical model. If we look at the modeling cycle, we formulate a problem, compute it using our unit circle, interpret the results, and validate. Because the unit circle extends our angles beyond just a single physical triangle to all real numbers, we can use it to model incredible real-world periodic phenomena. We're talking about the precise swing of a pendulum, invisible sound waves, or even the changing ocean tides.
See how our model evolved from a rigid 8th grade shape into a fluid high school tool? Standard right triangle trigonometry is limited, right? It only works for acute angles trapped inside a physical shape. But the unit circle, it completely breaks those boundaries. It extends those same proportional ratios to all real numbers, allowing for continuous, infinite rotation. It's a real game changer.
Section 6. Recap and transfer question.
Let's lock in what we've built today before I leave you with a final challenge to test your newfound understanding. The absolutely crucial takeaway from this explainer is that trigonometry isn't some entirely new, disconnected set of rules you have to memorize. No way. It is fundamentally just similar right triangles, ruled by the Pythagorean theorem, spinning endlessly on a coordinate plane. It is one continuous, beautiful, and coherent model.
Which brings us to our transfer question. Think about what happens when our triangle spins past a full circle. Since the standard circle is 360 degrees, how does our unit circle model handle an angle of, say, 400 degrees? Where does the triangle end up, and what does that tell you about the cyclical, periodic nature of trigonometry? I'll leave you to puzzle over that one. Thanks so much for learning with me today, and I'll see you in the next explainer.